Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on February 17, 2026, just yesterday. It presents GLM-5, a next-generation foundation model designed to bridge the gap between simple code generation and autonomous agentic engineering, achieving state-of-the-art performance across major benchmarks. The paper is titled GLM-5, From Vibe Coding to Agentic Engineering, and as we'll see later, the results on long-horizon tasks are really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. Alright, Figure 1 breaks down these performance claims across 8 demanding benchmarks, comparing GLM-5 against heavyweights like DeepSeek v3.2, Claude Opus 4.5, and GPT 5.2. Looking at humanity's last exam in the top left, the model achieves a score of 50.4 with tools, which is a significant margin over the others that sit around the mid-40s. Down in the bottom left, the browse comp results are equally striking, where GLM-5 takes the lead with a score of roughly 76%. It also holds its own on coding standards like SWE bench verified in the top row, delivering performance that rivals the best proprietary systems available. Moving to a broader view, Figure 2 presents the Artificial Analysis Intelligence Index. This chart aggregates performance across 10 different evaluations to give a single holistic score. You can see GLM-5 in the 4th spot with a score of 50, effectively tying with Claude Opus 4.5. The blue arrow traces its progress, marking a significant jump from the previous version, GLM 4.7, which sat at 42. This makes GLM-5 the first open weights model to ever reach a score of 50 on this index. Well, beyond just answering isolated questions, we need to know if these agents can plan over time. Figure 4 explores this through long-horizon tasks, starting with Vending Bench 2 on the left. This simulation challenges models to run a business for a full year, and the graph tracks their accumulating bank balance on the vertical axis. The pink line represents GLM-5, which climbs steadily to over $4,400, beating other open models and nearly catching Claude Opus 4.5. On the right, the CC Bench V2 panel breaks down specific engineering capabilities. Comparing the dark blue bars to the light blue ones, we see a 26% jump in front-end build success rates, showing that the model is becoming much more capable at end-to-end development. To understand how they achieve this, Figure 5 maps out the overall training pipeline. On the left, the base model training begins with a massive 27 trillion token corpus, but the key shift happens in the mid-training phase below. Here, they progressively expand the context window from 4,000 tokens up to 200,000. Specifically focusing on long context agent data. Then, looking at the post-training on the right, the team implements a sequential reinforcement learning strategy. It moves from reasoning reinforcement learning to agentic reinforcement learning, and finally to general reinforcement learning. To keep the model stable during this process, that large gray block represents on-policy cross-stage distillation, which prevents the model from forgetting earlier skills as it learns new ones. So diving into the architectural trade-offs, Table 1 compares the efficiency of multi-latent attention against the standard grouped query attention baseline. Looking at the first 2 rows, we see a problem. While standard multi-latent attention saves memory, its performance on code generation drops significantly, falling from 38.5 to 33.5 on human eval. To fix this, the team introduces MoE split, an optimization that updates attention heads at different scales. The 3rd row shows how this restores performance, boosting the MMLU score to 62.5, which actually beats the baseline. Consequently, the final model, shown in the bottom row, adopts a variant called MLA 256 with MoE split to balance this high performance with lower decoding costs. Well, Figure 7 illustrates 2 key reasoning strategies, interleaved thinking and preserved thinking. On the left, under turn 1, we see interleaved thinking, where the model generates a blue reasoning block before every tool call. This ensures the agent plans its logic step by step. Then, the right side compares memory handling for the next turn. The middle column shows the standard approach where past reasoning is discarded. In contrast, the far right column shows preserved thinking, which retains those reasoning blocks in the context, so the model remembers exactly why it took previous actions. Wrapping up, 2 takeaways stand out. GLM-5 successfully moves beyond passive code generation to true agentic engineering, proving that open models can now handle complex, long-horizon tasks. By combining efficient architecture with asynchronous reinforcement learning, it provides a powerful new tool for autonomous software development. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.